All right, just as with double integrals, Fubini's theorem is going to tell us that we're able to compute triple integrals by computing an iterated integral. And the iterated integrals go in exactly the same way that they do with double integrals. You've just got three variables to take care of, and just focus on the same logic as you're computing these. When you're integrating with respect to x, both y and z are treated as constants. Okay, and we can also then extend from integrating over rectangular boxes to integrating over general three-dimensional regions. And this gets a little bit more complicated than double integrals. So I wanted to pause and say something about our type 1 three-dimensional regions, type 2 three-dimensional regions, and unfortunately we have a type 3 as well. And actually, even within those individual types, there are sort of different ways to express the regions. So let's start with a type 1 region in 3 dimensions. And remember, since we're integrating 3 variable functions, we are integrating over such regions. So think about how I could describe a solid region in 3 dimensions. If it's sort of shaped like this, then what I could do is I could have the x and y coordinates ranging over some 2-dimensional region in the domain. The 2-dimensional region in the xy plane, and then the z coordinates corresponding to any particular xy point in the region D could be at highest this surface and at lowest this surface. So I could select any xy pair in D, and then I could allow z to range in between those two surfaces. So let me write that out in inequalities. Z at most is this surface, u2xy, and z is at least u1xy. And then, these together would describe this solid region. Of course, I know that describing xy in a 2-dimensional region can take a number of different forms, right? Like if I have this 2-dimensional region defined as a type 1 in the double integral section, so imagine that like x ranges between a couple numbers, and then y ranges in between 2 functions of x, g1 of x, g2 of x, then this would be one possibility of how a type 1 solid is expressed for purposes of computing a triple integral. So the region in the xy plane is expressed as type 1, and then z ranges between these two surfaces. So this is one option of expressing a region of this type. Of course, I could have the region D expressed instead as a type 2 region. What would that look like? Well, the y value would be going between 2 numbers. The x would be going between 2 functions of y. And then, of course, here the z still is going between these 2 surfaces. Let me say something about what the triple integral would look like in either of these cases. So if I had a type 1 region expressed in this way, then this is the order of the iterated integral that I would compute. On the very outside, I would have the x's ranging from a to b, and the y's ranging from these functions g1 to g2. That's just as the normal double integral is set up. And the very inner integral is going to have z going from u1 up to u2. I'm running out of space here, so you can put the inputs in there for those 2 functions. And if I list out the correct order of the differential units, that means z comes first, then y, then x. And then you have whatever your integrand function here is, your 3-variable f function, let's say. Over here, you would have c to d on the outside for y, h1 of y and h2 of y for x, and then your z is going to go again in between u1 and u2. Your order of integration has z first, whatever your integrand function is here, then x next, then y last. So as you can imagine, depending on which type of three-dimensional region I'm looking at, I'm going to have this same thing play out for each of them. So I have two different ways to express a type 1. I'm going to have two different ways to express a type 2 and two different ways to express a type 3. And that's precisely the number, that'll be 6 total, and that's precisely the number of ways that I can permute dx, dy, and dz in the triple integral. So when we encounter three-dimensional regions, we just have to decide which of these types is the best way to express the region. And as you recall from the double integral section, sometimes a two-dimensional region was described to us in, let's say, like type 2, and it was advantageous to re-describe it in type 1 because the integrand was easier to deal with. So the same thing could happen in triple integrals as well. I'm going to go ahead and fill out the corresponding orders that I would have with type 2 and type 3, and then in the next video we'll work some examples.